SpaceX is attempting. Something aerospace engineers once considered impossible in modern aerospace history. Catching a skyscraper-sized rocket out of the sky. And the terrifying reality is that it was never actually a choice, because hidden behind the spectacle is one of the most unforgiving equations. At the heart of aerospace engineering lies a principle so fundamental and so unforgiving that it has dictated the shape and fate of every launch vehicle ever built. This principle is not a matter of material science or engine performance, but of pure mathematics, articulated over a century ago in what is now known as the Tsiolkovsky Rocket Equation. To understand why SpaceX is compelled to catch its towering super heavy booster, a maneuver of unprecedented mechanical risk, one must first understand this equation, not as a formula, but as an immutable law of nature. It governs the relationship between a rocket's change in velocity, delta, its engine efficiency, and most critically, the ratio of its initial mass to its final mass. The presence of a natural logarithm in the equation is the source of its power and its cruelty. It ensures that the relationship is not linear, but exponential. This creates what engineers have termed the tyranny of the rocket equation, a condition where every kilogram of non-propellant mass, or dry mass, added to the vehicle requires a punishingly larger amount of propellant just to carry it. For a mission to Mars, which demands a colossal delta budget, this tyranny becomes absolute. The logic can be understood through a simple analogy. BOT, one of the everyday analogies used to distill complex physics. Imagine packing for a multi-day hike, where your destination is fixed. The weight of your empty backpack, tent, and gear represents the rocket's dry mass, while your food and water represent the propellant. To go farther, you need more water, but that water adds weight, which in turn means you need even more water just to carry the initial water. And you burn more energy, propellant, with every step. If the final payload, the scientific equipment you must deliver to the destination. The only variable you can ruthlessly optimize is the initial weight of your gear. SpaceX calculations, rooted in the foundational principles of astronautics explored at institutions like Massachusetts Institute of Technology, Aeronautics and Astronautics, show that adding a robust landing leg system to the Starship vehicle would be akin to choosing the heaviest possible backpack for the longest possible journey. The added dry mass would cascade through the Tsiolkovsky Rocket Equation, demanding exponentially more propellant and catastrophically shrinking the payload capacity, to the point where a self-sustaining settlement on Mars becomes a mathematical impossibility. The catch mechanism, therefore, is not an act of theatricality. It is an act of surrendering to physics. By offloading the entire mass and complexity of landing hardware from the flight vehicle to the ground, the exponential nature of the Tsiolkovsky Rocket Equation dictates that the mass of landing legs translates not into a linear payload reduction, but a mission-invalidating collapse of capability for interplanetary journeys. The architectural elegance of the Super Heavy booster lies in its extreme simplicity, a design philosophy dictated by the physics of mass. Structurally, the booster is best understood as a colossal stainless steel pressure vessel, a thin-walled cylinder whose rigidity is derived not just from its metal skin, but from the immense internal pressure of its cryogenic propellants. This principle is a scaled-up version of what can be called the soda can paradox, an everyday analogy illustrating that an empty aluminum can is easily crushed, yet a sealed, pressurized one can support significant weight along its vertical axis. The Super Heavy is optimized for one purpose: to withstand the immense axial compression of its own thrust during ascent. Its design is a masterclass in mass efficiency, where every element is dedicated to this singular, violent task. To introduce traditional landing legs onto such a structure would be an act of profound engineering compromise. The entire mass of the returning booster would have to be channeled from its cylindrical form into a few small contact points, introducing immense bending moments and concentrated stresses that the thin monocoque skin is simply not designed to handle. According to foundational principles of aerospace structural design, this would necessitate the addition of a heavy internal skeleton, robust rings, longerons, reinforced panels, creating complex load paths to distribute the forces of landing. This additional structure is parasitic mass. It contributes nothing to the ascent phase and therefore directly penalizes the vehicle's performance. Under the ever-present tyranny of the rocket equation, faced with this dilemma, SpaceX did not attempt to solve the problem on the vehicle. It moved the problem to the ground. The engineering trade-off was to transfer the entire complexity and mass of a landing system from the flight-critical booster to the stationary launch tower, giving birth to the Mechazilla concept. The tower, unconstrained by the need for flight, can afford to be massively over-engineered, equipped with powerful hydraulic systems and vast energy-absorbing mechanisms. This decision redefines the very nature of a launch pad, transforming it from a passive piece of infrastructure into an active, dynamic participant in the mission. It is a philosophy that accepts extreme complexity in a reusable, serviceable ground system in order to grant the flight article the purest possible design. By moving the entire landing apparatus from the rocket to the launch tower, the Super Heavy is engineered to remain a structurally optimized cylinder, maximizing its performance by shedding the parasitic mass of a landing system. The final moments of the Super Heavy booster's descent represent a physical problem of staggering scale, where the abstract mathematics of the rocket equation manifest as raw kinetic force. As the vehicle performs its final landing burn, it has already shed the vast majority of its orbital and re-entry energy. Yet the residual energy it carries into the capture zone is still enormous. This terminal challenge is twofold. First, the brute force dissipation of energy, and second, the surgical precision of the control system orchestrating the event. The task can be framed using one of the everyday analogies for complex physics. It is functionally equivalent to stopping a freight train moving at speed using only the advanced suspension system of a luxury car. The mass of the nearly empty booster is still immense, and even at its low terminal velocity, its kinetic energy must be absorbed smoothly and without destructive shock. The primary mechanism for this is the massive hydraulic system integrated into the Mechazilla arms and tower structure. These systems act as colossal shock absorbers, converting the sudden dynamic load of the catch into a controlled increase in hydraulic pressure, safely dissipating the kinetic energy as heat over a few critical seconds. Without this controlled absorption, the impact force would far exceed the structural limits of both the boosters, catch points, and the tower arms themselves. However, managing this energy is only half of the problem. The control system's challenge is arguably even more formidable. As it operates on a timeline with no margin for error, the booster, while guided by its engines and grid fins, is still subject to unpredictable atmospheric variables, wind shear, ground effect turbulence, and instability during its final meters of flight. The tower's control system must therefore track the vehicle's position and velocity vector in real time, predict its immediate trajectory, and command the massive steel arms to move to a precise intercept point, all while compensating for atmospheric disturbances. Control theory dictates that the latency in this feedback loop, the time between sensing the booster's position, computing the correction, and actuating the hydraulic arms, must be reduced to mere milliseconds. A delay of even a fraction of a second would result in a miss, leading to the catastrophic loss of the vehicle. This requires a seamless fusion of data from the booster's own avionics and ground-based tracking systems processed by computers that execute the maneuver with autonomous, inhuman speed and accuracy. The catch maneuver is therefore a simultaneous solution to a problem of immense force and a problem of infinitesimal precision. The successful capture of the super heavy requires dissipating the kinetic energy of a multi-ton object while executing a real-time control maneuver with sub-meter accuracy in a dynamic environment. The culmination of these interconnected engineering decisions, a design dictated by the rocket equation, a structure optimized by transferring complexity, and a capture system that masters immense force, is not merely a novel way to land a rocket. It represents a fundamental redefinition of the relationship between a launch vehicle and its ground infrastructure, signaling a new paradigm in aerospace operations. Historically, launch architecture has treated the vehicle and the pad as distinct entities with a temporary, transactional relationship. The launch pad was a static piece of critical infrastructure, a hold-down and fueling station that became inert the moment the vehicle cleared the tower. For previous reusable systems, recovery was a separate, logistically intensive process, involving ocean landings, transport, and extensive horizontal processing. The Starship and Mechazilla system dissolves this long-standing separation. It conceptualizes the super heavy booster and its launch tower as two halves of a single, deeply integrated machine, a closed-loop system designed for launch, recovery, and relaunch in one continuous process. In this new model, the tower is not passive infrastructure. It is an active, dynamic component of the flight vehicle itself. It functions as the booster's landing gear, its recovery crane, and its integration stand, merging three distinct and time-consuming operational phases into one fluid motion. This integration is the key to unlocking the ultimate goal of SpaceX architecture, a dramatic reduction in the turnaround time between launches by catching the booster and immediately having the ability to place it back onto the launch mount. The system aims to eliminate the most significant bottlenecks of traditional reusable rocketry. The primary constraint on reflight is intended to shift away from complex post-flight logistics and refurbishment towards the far simpler problem of refueling and system checkouts. This recontextualizes the high-risk catch maneuver as a calculated and necessary component of a much larger strategy, a strategy aimed at achieving an unprecedented launch cadence. The entire system is an engine for operational efficiency because the economics and logistics of establishing a self-sustaining presence on Mars are predicated on a launch rate and cost per kilogram to orbit that are orders of magnitude beyond current capabilities. The integration of vehicle and tower into a unified launch and recovery machine is the strategic linchpin intended to make interplanetary settlement a logistical and economic possibility. The spectacular and high-risk maneuver of catching a skyscraper-sized rocket is therefore not an act of choice, but the ultimate expression of engineering subservience to the unyielding mathematics of spaceflight. This unforgiving physical law forced the redefinition of the launch pad itself, integrating it into a single machine, architected for the singular purpose of making interplanetary colonization a logistical reality. The final design was never determined by a preference for how to land, but by the necessity of leaving Earth with enough mass to matter. If this deep dive into the engineering behind the headlines, is the kind of analysis you value, support Tech Dissect Official for more deep engineering analysis. Because at the edge of technological ambition, physics always gets the final vote. Given this radical departure from conventional design, do you believe the integrated launch and catch architecture will become the new standard for all future heavy lift vehicles? Or will it remain a highly specialized solution born from the unique demands of the Mars mission? Thank you for joining this analysis. Next time, We will investigate the monumental materials science challenges, standing between humanity and the dream of limitless energy, from nuclear fusion